This is the first lesson in topic 17. In this lesson, we're going to be looking at classifying polygons, which is just a review from what you learned in middle school, and develop formulas for finding the sum of the measures of the interior angles of a polygon and the measure of each interior angle of a regular polygon. So the first thing we need to remember is what is a polygon. So you can see we have two different groupings of figures here. In this first box, these would all be considered polygons. But in this group, these are not polygons. So this helps us see the difference in what it takes to be a polygon. So the reason why this figure is not a polygon is because of the curved edges. Polygons have to be made up of segments only. The reason this figure and this figure are not polygons is because there's overlapping of the segments. And so the segments cannot overlap in a polygon. And here we have an open figure. A polygon has to be closed. So a polygon is a closed figure made up of line segments that do not overlap. Those are the three things that we have to remember for it to be a polygon. Now, we sure have studied a lot about triangles, but that's only one type of polygon, and we have many more that we're going to be looking at. But this topic 17 mainly focuses on quadrilaterals, but we're going to look at some properties of polygons in general before we get to quadrilaterals. All right, so remember the bridge picture we looked at way back in topic 1. We really talked about all the different polygons that are part of this bridge and different figures, and even parts of figures like points and segments and lines. But you will see the quadrilaterals in this bridge, and that's what we're going to be focusing on. So let's look at this first animation to look at the parts of a polygon. First of all, just make sure you're caught up on your notes here. These are the polygons in the first grouping, and these are non-polygonal figures here, so non-polygons. And then we just have the definition of a polygon on number 2, made up of line segments. They intersect only at their endpoints, which means they don't overlap. So you might put that means there's no overlapping. And they have to be closed. Those are the important parts there. All right, so let's look at this first animation. So first of all, polygons have sides, and their sides are segments. So remember, to name a segment, you have to put the segment bar above the two endpoint names, and always use capital letters for those points. The vertices are the points where the two segments join together, and so you can see that this polygon has 6 of them, A through F. Interior angles, of course, are angles that are inside the figure. But we also, and we've talked about this before, have what we call exterior angles. Remember, an exterior angle is formed by extending out one of the sides of the polygon. So you can see the extension of one of the sides creating those exterior angles. Diagonals, remember, are segments that join two non-consecutive vertices. So when we join two that are consecutive, like A and B, we make up a side of the polygon. But when we connect two that are non-consecutive, like A and C, that's where we create a diagonal. And again, diagonals are segments, so you would name them with segment bars, and they're two endpoints. All right, so all polygons have an interior and an exterior. And we need to know the difference between a convex polygon and a concave polygon. So in a convex polygon, all of the diagonals are going to be inside the figure, but with a concave, you're going to have at least one diagonal that is outside the figure. So you can see in the convex, every time we join two non-consecutive vertices, that segment's inside. With the concave, when we get to this last one, that segment's outside. And so if a diagonal is outside, that means that figure had to be concave. Also, in a convex, all of the interior angles have to be less than 180 degrees. In a concave, you're going to get an angle here, you can see this one right here, that is greater than 180 degrees, and that's called a reflex angle. So concave polygons will have at least one reflex angle that is more than 180 degrees. So you should have question 3 completed in your notes here. Name a vertex. So the vertices are just points. So point A is a vertex. Naming the polygon, you just name them in a consecutive order. It doesn't matter which point you start with or which direction you go. You just have to be consistent. So you couldn't name it A, D, B, E, F, C, like all over the place. If you start with A and your next letter is B, then you have to continue along in that same order. So I'm just going to name this A, B, C, D, E, F. Naming a side, don't forget your segment bar. So segment AB is one of the sides, capital letters with the segment bar. Name an interior angle. Remember to use your angle symbol and any capital letter. And we can name these with just one letter because there's only one angle that has A as a vertex. If we named it with 3, we would name it angle BAF or angle FAB. Naming a diagonal, remember that's a segment that joins two non-consecutive vertices. So like segment AC would be an example of a diagonal. All right, look at question 4 in your notes. Polygons are classified by their number of sides. And so we have special names for the polygons that have sides 3 through 10. And then we have one that has 12 sides. And then after that, we just start calling it like a 14gon. They have names, but just nobody commits those to memory. It's just too much. So if a polygon has 22 sides, we call it a 22gon polygon, and gon means sides. That's what that means. So each of these that are pictured here, and you're familiar with these prefixes from former math classes, so those are kind of in a different color there just to let you see the prefixes telling you how many sides. So tri we know means 3, oct we know means 8. So in each one of these polygons, all of the sides are congruent and all of the angles are congruent. And so we call those regular polygons. So anytime you see the word regular, that is telling you that the figure is equilateral and equiangular, meaning all the sides are congruent and all of the angles are congruent. Now with a triangle, if the sides are congruent, we know the angles have to be congruent. But with all these other polygons, just if it has one of these qualities, it doesn't mean it has the other. So for instance, you can have a four-sided figure that is equilateral and not equiangular. We call that a rhombus. And you can have all of these that is equilateral but not equiangular. And so you can see in this diagram here, these are all regular polygons. These figures have all equal sides, but they do not have all equal angles. So these are irregular polygons here. So here are some other examples of irregular polygons in this drawing here. So let's look at your notes. Make sure you have these labeled here. A 3-sided figure is a triangle. 4-sided is a quadrilateral. 5 sides is a pentagon. 6 sides is a hexagon. 7 sides is a heptagon. 8 sides is a octagon. 9 sides is a nonagon. 10 sides is a decagon. And 12 sides is a dodecagon. So you can pause this if you need to get those down. All right, so in this topic, we're going to be looking at how to classify polygons. And so to do so, there's going to be lots of things, all characteristics that we're going to be looking at. So for example, we're going to be looking at how many sides they have. And are those sides congruent or are they parallel? How many angles are there? Are any of them congruent? What is their sum? How are the interior angles and exterior angles related to each other? Looking at the diagonals, are they all interior or are some of them exterior? Are the diagonals congruent? Do they bisect each other? Are they perpendicular to each other? So these are all things that we're going to be looking at in topic 17. All right, so floor tiles and pavers that you see in houses and outside patios maybe are often in the shapes of regular polygons. Remember, regular means all sides are congruent and all angles are congruent. So sometimes a single tile is used, like in this blue one here. That's a hexagonal or hexagonal flooring where all of the tiles are hexagons. and they are regular ones. But sometimes you use different polygons together to make a design, like we have here. So we have some squares, and then we have some 1, 2, 3, 4, 5, 6, 7, 8-sided figures, so octagons, put together to make a tile flooring. So remember that the measures of the angles in a triangle always add up to be 180 degrees. We're going to use that fact to help us to find the interior angle sum of other polygons as well. So here we have an 8-sided figure, which remember is called an octagon. Right now it's regular. All of the sides are congruent and all the angles are congruent. Notice that I can show triangles formed inside this figure by simply drawing all of the diagonals from a single vertex. So these are not all of the diagonals for the figure. They're all the ones that I can draw from one point. And so notice when I draw the diagonals how many there are. There's 1, 2, 3, 4, 5 from one point. There's 8 sides, 5 diagonals from one point. How many triangles are formed? 1, 2, 3, 4, 5, 6. Well, remember, each one of those triangles has a sum of, oh shoot. Okay, sorry, I thought our video stopped, but it didn't. So each one of those triangles has 180 degrees. So we can just take the number of them, which is 6, and multiply by 180. And that tells us that the sum of all of the interior angles of this octagon are 1,080 degrees. Now this is a regular octagon. What if I make it irregular? Did that change the interior angle sum? It's not affecting it, is it? So that is the interior angle sum for any octagon, not just a regular one. So with any octagon, if you draw the diagonals from one vertex, you're going to have 5 of them. That's the number of sides minus 3, right? 8 minus 3 is 5. But you form 6 triangles. So that's the number of sides minus 2. So let's look at another figure. Let's go down to a pentagon. So it's starting off regular. Notice how many diagonals are drawn from one point. 2 of them. Remember, that's the number of sides minus 3. The number of triangles that are formed is 3. That's the number of sides minus 2. Each one of those triangles has 180 degrees. So 3 times 180 tells me all of the angles of a pentagon have to add up to be 540 degrees. Again, that's not just a regular pentagon. That's any pentagon. The 5 angles will add to 540 degrees. Let's go up to the dodecagon, which has 10 sides. How many diagonals would it have? Remember, the number of diagonals from a single point is always the number of sides minus 3. So there should be 7 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9. Sorry, this is a dodecagon, which has 12 sides. 12 minus 3 is 9. I thought I was doing a decagon. All right, so the number of triangles should be the number of sides minus 2. So we should have 10 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Good. And each one of those triangles has 180 degrees. So the sum of all of the angles, the interior angles of a dodecagon, is 1,800 degrees. Again, that's going to be the same with a irregular dodecagon too, not just regular ones. All right, so let's look at question 6 in your notes. It says divide each polygon into non-overlapping triangles. What pattern do you see? So the number of sides in this figure is 1, 2, 3, 4, 5. Remember, that's called a pentagon. When we draw the diagonals from a single vertex, we can draw this one and this one. That's it. So there are 2 diagonals. Remember, the number of diagonals is always the number of sides minus 3. 5 minus 3 is 2. The number of triangles it has is 3. That's always the number of sides minus 2. So the number of sides of this figure, 1, 2, 3, 4, 5, 6, 7, 8. So it's an octagon. The number of diagonals should be n minus 3, which is 5. So let's go from this vertex. Here's 1, 2, 3, 4, 5 diagonals. And the number of triangles should be n minus 2. 8 minus 2 is 6. 1, 2, 3, 4, 5, 6. The next one looks like it might be a square, or at least a rhombus. The number of sides is a 4, so it's definitely a quadrilateral. So the number of diagonals it should have, 4 minus 3, is only 1. So from this vertex, I can only draw 1 diagonal. Number of triangles, 4 minus 2, is only 2. So 2 triangles. And finally, well, we'll have to start